Okay, in this example, we're looking at the buoyant forces on a fully submerged boulder. We're told that a large boulder is being vertically moved. We're not told if it's up or down, but it's moved off the side of a ship using a winch and cable. The boulder has a density, which is given as 2.6 grams per cubic centimeter, and a volume of 112 cubic meters. If the tension in the cable is 3.35 million newtons, then what is the direction and magnitude of the acceleration of the boulder? Okay, so we have to set up a free body diagram and think about what's going on with this problem. Okay, so here is going to be the picture for the setup. I have done a pre-calculation here showing the mass of the boulder because we're given its volume and its density, so of course we can easily get its mass that way, and I figured it would be useful, so I went ahead and calculated that right away. And we have some forces drawn here. We have the buoyant force drawn, the tension force, and the gravitational force. Since we're not worried about torques, I am not worried about the location of the force vectors. There are no moment arms, so I was a little bit loose about where I put the vectors, just to clearly show them, so I drew them apart. Okay, so let's think about this, right? We're given a value for the tension, and we have a value for the gravitational force. So these are our known quantities. We can solve for the buoyant force pretty easily by thinking about the displaced water, and that will be one of our first steps. And then ultimately what we're really trying to solve for is the acceleration. And I have here that the acceleration is going to be up. Okay, but let's prove that, right? So that's going to be the result, but let's actually show that it is indeed positive in the positive y direction and exactly how positive it is. Okay, so let's write our sum of forces in the y direction. So this will be for part A. So F net y. Okay, so we got our two upward forces, the buoyant force and the tension force. We have the downward gravitational force, and this is going to be equal to the mass of the boulder, m, times that unknown acceleration. And I don't put a plus or minus here because we're actually solving for a, and when of course we'll find its sign when we solve for it algebraically. Okay, so let's expand our terms here. All right, so that's be our next step. F net. Right, and this is the y direction. That clear? And you got to be real careful with this problem, especially because we're trying to solve for whether acceleration is up or down. Make sure you define what the positive direction is. And here I of course said positive y is upwards. So the buoyant force, by definition, is the density of water. All right, so density of the fluid times gravity times the volume displaced. So we'll call that V disp for displaced. The tension force, that's just a value that we're given, and then here we just have mg and then ma. Okay, well, since the boulder is fully submerged, right, because we have here vertically moved on the side of a ship, then we know that the volume displaced is equal to the volume of the boulder, which is given as 112 cubic meters. It's worth pointing out too that when I made the conversion from grams per cubic centimeter to kilograms per cubic meter, I factored by 1,000. And that's because although there's 1,000 grams in a kilogram, there are 1,000,000 cubic centimeters in a cubic meter, which is where we got this value here of 2,600 kilograms per cubic meter. All right, so let's plug in what we have here. So we're going to have the density of water. All right, so that's going to be 1,000 kilograms per cubic meter. That's just rho f. And our 9.8 meters per second squared. Then we have our volume of 112, and that's going to be, actually here, you know what, I'm plugging in my values too soon. Let's keep this symbolic. I don't know why I was throwing in numbers already. Okay, so let's just make one substitution here where I'm just going to point out. I think that's what I had mine here. I just wanted to point out that this is equal to the volume of the object. All right, or we'll call it the boulder, because fully submerged. Okay, but now let's do some algebra before we plug in values. Okay, so, all right, let's just move on then. So we have our acceleration is going to be, well, we have rho f g v minus ft minus mg all divided by m. All right. I won't bother to distribute the m because it would only simplify one of the three terms, and the other ones would just end up with m's in them in the denominator. Okay, so then if I actually plug in values here, now we're going to have 1,000 kilograms per cubic meter, 9.8 meters per second squared, times our volume of 112 cubic meters, minus our given tension force of 3.35. Plus, right? You've probably been wondering why, right? It should be plus all along, because of course the tension points upwards. All right, it has to. Tension is always going to point upwards, even if the acceleration is downwards. The tension still points upwards. So, key thing there. So sorry for the confusion. And then we have our given value. It was 3.35 times 10 to the 6. All right, newtons. And then minus the gravitational force, which is just so 2.91 times 10 to the 5 kilograms, and then times 9.8 meters per second squared. Okay, and that's all going to be over 2.91 times 10 to the 5 kilograms. Okay, it's I guess it's 2.912. So I'll go ahead and put that full value in the calculator. Okay, but let's see what we get now for our acceleration. And if it indeed is positive, as I claimed in the figure, okay. So we'll set up the numerator. So 1,000 density of water, gravity, right? And then plus 3.35, and then times 10 to the 6th, all right, and then minus the gravitational force, all right. And it makes sense that the buoyant force and the tension force, right, are being opposed by the gravitational force, right? Because if it's really massive, then it's going to accelerate downwards. Or if the tension is too small, for example, right? If you're just not keeping that cable taut enough with the winch. All right, so 2.91. 2, okay, times 10 to the 5th, all right, and then multiplied by 9.8, all right, and then that's all going to be divided by just the mass, so 2.912 times 10 to the 5th. Okay, so close parentheses there. All right, so I get 1.74 if I'm running to three significant figures. Oh, but I made a mistake here, right? I have a plus where I should have a multiplication right here, right? It's not plus 9.8 because we're trying to turn that into a force. So you have to multiply volume by gravity times density. So this should be multiplication. There we go. All right, so 5.47. All right, 5.47 meters per second squared. And here we'll color code this as our upward acceleration in the figure. All right, so there it is. There's the answer to part A. All right, and obviously part B is just quite similar, although we're just going to show that we're going to get a negative acceleration, so I'll just quickly run through that. All right, so part B, we just, everything's the same, how fast and what direction we're asked. Would the boulder have to be accelerated in order for the tension to read 1.15, right? So before, we were actually pulling the rock up out of the water, and that required a certain tension. But now we say, okay, well, what if for example, the rope can only sustain 100 or 1.15, which would be 11,500 newtons of tension force. Well, in that case, the rock wouldn't come up out of the water; it would actually sink. It wouldn't sink as fast as it would without any tension, but it would still sink. And let's show that. Okay, so in this case, we're going to have the same setup. Okay. And so this is, we'll say, I'll go ahead and put a box around this since it's used for both parts of the problem. And so we'll just have slightly different values here. This part obviously being the same, right? Times 112 cubic meters. The only difference here is we're going to have our 1.15 times 10 to the 4 newtons. Then we get our same mass. All right. And then finally divided by 2.91 times 10 to the 5 kilograms. Okay, so with those values, let's go ahead and just change it in the calculator. We just have to make one small change. All right, so the difference is just this one here in the middle. It's instead of being 3.35, will be 1.15, and instead of 10 to the 6th, it's going to be 10 to the 4th, right? And still upwards. But look, now we get a negative acceleration. Okay, so there's our value, a negative 5.99 meters per second squared. Okay, so negative here, of course, tells us that it is downwards. All right, so color code that one as well. And I'll just point out that this one here is upwards because positive. And then here, downwards. Because negative. All right, so the sign of the acceleration definitely tells us our direction because we're consistent with our coordinates. Okay, well, thank you.